Hello everyone. Today we'll be presenting VL2 Virtual Layer 2 Scalable and Flexible Data Center Network paper. So these are the authors of the paper and it was published by Microsoft Research. We don't have a YouTube URL just yet, but we'll have that shortly in our final slides. So why are shared data centers important? So with the emergence of cloud services, shared data centers have become more common because they support a diverse array of utility computing operations and various unique applications. But even though they have various advantages, a conventionally designed data center hinders with agility and are inflexible due to their reliance on expensive hardware, their tree-like structure design, and their routing design. So, given said that, why do we still prefer, if there are issues with shared data center, then why do we still prefer them? Because they have various other benefits and other costs. And we'll talk about various benefits that they have and the costs associated with them. So there are many economical and technical reasons behind why shared data centers are preferred over standalone data centers. So some of them are that with shared data centers, we can do bulk deployment of various services at scale, which results in cost saving, and we can do dynamic reallocation in case of load changes or in case of equipment breakdowns. The reason these are doable in a shared data center is because we have extra servers that we can rely on, whereas in standalone data centers, we don't have extra servers to rely on. But since we have extra servers or a high number of servers, in a shared data center, high costs are involved. So for example, a 100,000 server data center can cost up to $12 million per month. So it is essential to make sure that high profitability is achieved, which is dependent on maximum utilization and which can be achieved, or maximum utilization can be achieved through agility, and it will also improve our risk management in our shared data center. So what are the issues and challenges that we face in our conventional data centers? So currently the routing designs for conventional data centers achieves scale by assigning servers topologically significant IP addresses and dividing the IP addresses or dividing the servers among VLANs, virtual area local networks. So this results in fragmentation of the address space and limits the utility of virtual machines. And it can also impact a service negatively if other services are taking more resources. So all this contributes to inflexibility of data centers network and hinders overall agility, which will decrease our profitability. And like we just discussed, since the cost of maintaining a shared data center is so high, achieving high profitability is essential to make sure that shared data centers function. So the proposed solution, the paper proposes the solution that data center network needs to utilize more concrete model to maximize traffic flow, and that the data center management software should be easily able to assign any server to any service with any IP address that the service needs. This results in no disruptions on the client end, even if the service is redeployed on a new server. So to overcome these limitations, VL2 network architecture for data center will help us and will help us achieve these high profitability through three objectives: high uniform capacity, performance isolation, and layer 2 semantics. And how do we achieve these things? We'll talk about that later in the slides. So what is VL2 network architecture? So VL2 network architecture is designed to be deployed today in existing data center infrastructure, which will minimize cost. And in order to achieve this, VL2 proposes that we merge layer 2 and layer 3 into a new layer called virtual layer 2, VL2. And this is done by using three techniques: flat addressing for layer 2 semantics, load balancing, sorry, Variant load balancing for uniform high capacity between servers, TCP to ensure performance isolation. And as we can see on the right, this is our topology of a VL2 architecture. Um, and in a minute, we'll see how it compares to a traditional data center design. So this is a traditional data center design on the right side. And this, as we can see, it has a more of a tree-like structure to it, which basically will result in bottlenecks as we go up the hierarchy of the tree. So the problems with today data centers is that it has limited server-to-server capacity due to higher number of switches and routers and oversubscriptions. As we move up the hierarchy, the number of servers decreases, which leads to oversubscriptions. Then there is fragmentation of resources, which occurs by nearby servers in the hierarchy are grouped together. So in case of failures, all the servers go down, which is usually not good. And we should always have redundancies in shared data centers. Then excess capacity being reserved by individual services in case of failures and high traffic. And poor reliability and utilization is occurred because one-to-one reliance model limits each device to run at most at 50% capacity. And the spanning tree protocol in layer 2 allows at most 2 paths between network switches. So all of this results in further bottleneck of the data center's network. So since we know the problem with our existing data centers, what we will do is we'll try to analyze the live production data um, and see what patterns we can learn, and then try to find a solution that solves all of our problems. So in this experiment, the paper did a 1500 node cluster experiment where the node transfers petabytes of data, which are distributed over 75 TOR switches. And this resulted in seeing that the TOR switches uplinks were, some of the TOR switches uplinks were about at 80% utilization, while the other uplinks were not being utilized at all. So this is not uniform distribution, and VL2 will address this. The second thing we noticed that the server-to-server traffic compared to the traffic entering and leaving the entire data center has a ratio of approximately 4:1. That means that server-to-server communication is happening 4 times more than the traffic entering and leaving the data centers. So it's very essential to have efficient server-to-server communication within a data center network. The second analysis was flow distribution analysis. As we can see on the right side graph, most of the time the distribution is uniform, but there are certain spikes. And this is due to the fact that data centers are an engineered environment which have been designed with careful design decisions. So most of the times they are able to uniformly distribute traffic, but in certain cases of spikes, they fail to do so. This is where VLB, variant load balancing, will come into the picture, as variant load balancing will dynamically route traffic in real time based on the network conditions, which in a data center are constantly changing. So since VLB dynamically routes traffic based on the network conditions, it will outperform other adaptive routing schemes and will increase our efficiency of the data center network. The third analysis that was performed was on the traffic matrix of those 1500 node server clusters to learn a few simple patterns and try to be efficient, capacity efficient for most traffic. So the traffic matrix indicated that there is randomness involved in data center traffic, and there weren't any patterns that we could leverage or learn. The reason being is data centers are designed to use randomness to improve performance. Hence, it is better to move away from randomness and use VLB, which will check the network status and route traffic accordingly. Failure characteristic analysis. So this was the fourth analysis and the last analysis done, where they collected logs from 8 different data centers hosting 100 different services. to see what kind of logs, what kind of errors or failures they typically see. And from these logs, it was revealed that most of the failures occur in small size. But if there is a downtime in data center downtime involved, then the impact can be significant on a global scale, depending on how much traffic is being routed via that shared data center. The common causes of downtimes involve network misconfiguration, firmware bugs, and faulty equipment. So, after applying one-to-one redundancy in the case of networking equipment failure, in 0.3% of the failures, all redundancy equipment becomes unavailable. And so this is where VL2 will try to broaden this approach and move away from one-to-one redundancy and move to an end-to-end dynamic redundancy. The end-to-end numbers will be decided depending on the total amount of servers available in the shared data center. This will result in the impact of failures being muted because there are uh, additional servers to handle in case of end-to-end redundancy, whereas in one-to-one redundancy, if one server fails, then it will result in no redundant equipments being available. So these were all the analysis that were done on the data. And next up, Nikhil will talk about the further sections of the paper. Thank you, everyone.
Before we look at design principles of VL2, let's look at the observations that the authors have made while collecting measurements in the data center. A machine in the data center typically has around 10 concurrent flows, known as mice flows, for more than half of the time. However, around 5% of the time, it may have more than 80 concurrent flows, referred to as elephant flows. These large flows can create network congestion in hotspots, leading to a performance degradation. Due to the high volatility and divergence of data center traffic, it can be challenging to predict how traffic will behave within a given interval. This unpredictability highlights the need for robust traffic management solutions that can handle fluctuations in traffic and prevent congestion hotspots. In traditional networks, routing is accomplished by dividing servers into VLANs, with each VLAN having its own unique IP addressing scheme. However, if a new server from a different VLAN needs to be assigned to a service, it can be a time-consuming process that requires a lot of configuration changes. The network must also inform the application about the address of the new VLAN and the IP of the new server within this VLAN. This can significantly impact the speed of the deployments. VL2's primary goal is to achieve agility by providing an abstraction that allows all servers assigned to a service to think that they are directly connected to a single server. This approach enables the assignment of any server to any service, eliminating the need for the application to worry about the assignment process. When the application sends a message to a set destination address, the network takes care of delivering the packet to the correct destination, even if the destination has been reassigned or changed location. In addition, VL2 aims to maintain uniform high capacity and performance isolation through load balancing. This objective is achieved using two specific addressing schemes: application-specific addresses and location-specific addresses. Furthermore, VL2 utilizes variant load balancing and class network topology to achieve this goal efficiently. In traditional networks, aggregator switches are typically connected to only two intermediary switches for fault tolerance, resulting in a maximum of two possible paths from source to destination. This limits the bisection bandwidth utilization at an aggregator switch and causes a 50% reduction in case of intermediate switch failure. In contrast, class network topology employed by VL2 uses a bipartite graph between aggregator and intermediary switches. If an aggregator switch is connected to n intermediary switches, the failure of any one of them only decreases the bandwidth by a factor of 1 by n, resulting in an efficient bandwidth utilization. VL2 uses variant load balancing scheme to efficiently balance traffic load across multiple paths. Its routing algorithm involves taking a random path up to a random intermediary switch and then taking a random path down to the destination top of the rack switch. To ensure fault tolerance and high availability, VL2 assigns the same anycast address to all intermediate switches. This simplifies the updating process in case of link or switch failures. The directory system returns this anycast address to VL2 agents, and when packets are encapsulated with this address, the ECMP protocol ensures that they are delivered to any active intermediary switch. One of the advantages of VL2 is that it is designed to be backward compatible with existing data center networks. This means that VL2 can be implemented in a data center that is using a conventional network architecture without requiring a complete overhaul of the existing infrastructure. VL2 achieves backward compatibility by using the same physical layer as the existing network, which means that the same switches and links can be used. So there is no need to introduce new hardware like switches or interfaces. However, VL2 agents that sit on every server's network stack introduces a new logical layer on top of the existing physical layer called shim layer. This approach allows data center to gradually transition to VL2 without incurring significant costs or downtime. Although VL2 is not designed to directly interact with external traffic, the border gateway control routers, otherwise called BGP routers, route the external traffic into the data center network. Once the traffic is inside the network, VL2 takes care of routing. Therefore, it is also compatible with internet traffic from outside the data center. VL2 uses two different addresses to locate nodes in a data center network, namely location-specific addresses and application-specific addresses. All the switches and interfaces in the network operate on location-specific addresses. They use an IP-based link state routing protocol to route the packets. Remember that we have seen link state routing in the beginning of the class in the semester. Applications use application-specific addresses. This address remains the same regardless of VM migration or reassignment. The typical packet traveling from top of the rack switch to an intermediary switch would be encapsulated as shown in the illustration. The payload is attached to application address, and then an additional header called location address is added to the packet. More on packet forwarding in the next slide. As previously mentioned, the VL2 agent resides on the network stack of every server and captures outgoing packets, encapsulating them with location-specific addresses of the destination top of the rack switch. To determine the destination TOR address, VL2 utilizes a directory system that maintains mappings between application-specific address and location-specific addresses. When VL2 agent requires the location address for a specific application address, it queries the directory, which promptly returns the corresponding application address. VL2 agent then catches the mapping for faster future lookups. After adding the location address, the agent routes the packet to the TOR switch, which randomly selects an intermediate switch and forwards the packet to it. The intermediate switch then decapsulates the packet, reads the destination TOR's location address, and forwards the packet to the destination TOR. Finally, the TOR switch decapsulates the packet again, reads the application address of the server, and delivers the packet to its destination server. VL2 proposes several key features that improve the performance, scalability, and flexibility of the data center networks. First, VL2 replaces hierarchical topologies with a class network topology. This architecture enables efficient routing and load balancing of traffic within the data center network. Second, VL2 employs variant load balancing to deal with volatility in traffic. This reduces the impact of congestion in the network. Third, VL2 uses existing routing and forwarding protocols such as OSPF, Open Shortest Path First, and Equal Cost Multipath ECMP. This approach ensures that VL2 can be used in existing hardware without requiring a complete overhaul of the network infrastructure. Fourth, VL2 uses name and location specific separation using application address and location addresses. This two-level hierarchical addressing scheme enables efficient routing and load balancing of traffic within the data center network. Finally, VL2 uses a two-tiered directory service for address resolution, enabling fast and efficient lookups of address mappings within the data center network. Overall, these features make VL2 a powerful and versatile network architecture that is optimized for the demands of modern data centers.
Following this, the paper now discusses the performance of VL2 in terms of its output, latency, and scalability. Evaluating the performance of VL2 can help us identify its strengths and weaknesses and guide us for further development of network architectures in data centers. And thus, it is of crucial importance. So we will evaluate the performance of VL2 on a prototype that consists of 80 servers. And this test bed is built using the class network topology. We first investigate VL2's ability to provide high and uniform network bandwidth between servers, which is the first point. Like, does it provide uniform high capacity? Then we analyze the performance isolation and fairness between traffic flows. It means that if the network is able to provide these in case of high traffic flows. And finally, we measure the convergence after link failures. One of the key features of VL2 is that it provides uniform high capacity throughout the network. Owing to this, VL2 enables applications to run more efficiently and effectively with faster data transfer speed and reduced latency. To test this feature, an all-to-all data shuffle stress test is performed, where all servers simultaneously initiate TCP transfers to all the other servers present in the network. So we consider a network of we consider 75 servers are present, and each of the servers transmit 500 MB data to each of the other servers. So this totals up to a shuffle of 2.7 TB of data. Observing the happenings of this event in the plot, we see that on the y-axis, we see that for the majority of the run, that VL2 is able to achieve an aggregate output of around 59 Gbps. Whereas on the x-axis, we can conclude that this total data shuffle of 2.7 TB takes a total time of 395 seconds. The important observation is that the output is evenly distributed among the flows throughout the run. After considering some sources of inefficiency in the prototype that affects the output, the result is that the maximum achievable output of the prototype that we are using is 62 Gbps. And from the test that we have performed, we are able to run and we are able to achieve an aggregate output of 59 Gbps. Hence, we state that the network sustains an efficiency of around 59 by 62, that is 94%. With this high obtained efficiency, we are able to demonstrate that VL2 promises to achieve uniform high bandwidth across all servers in the data center. Coming on to the further objective, the paper states that VL2 splits the traffic of the network uniformly among the intermediate switches. Now we are aware that all the flows pass through the aggregation switches. Hence, it is sufficient to check each of the aggregation switch for the split ratio among the links to the intermediate switches. So we have plotted the Jan's fairness index for traffic to intermediate switches as a function of time for each of the aggregation switch. From the plot, the fairness index for the split ratio for each of the aggregation switch averages to over 0.98. This evaluation validates that the architecture is providing to be an efficient mechanism for preventing hotspots in the data center network. One of the other primary objective of VL2 is agility, which is the ability to assign any server in the data center to any service. Now, to achieve this, there should be performance isolation between all the services, so that in case one service is under attack, the performance of other services are not impacted. The experiment which we have used to prove this is we add two services to the network. Service 1 has 18 servers, and each server starts a transfer to other server at time is equals to 0. The second service consists of 19 servers, and they start at, as you can see in the graph, at time is equals to 60 seconds, where initially only one of their server is present and the other servers in the service 2 are dynamically added over time. And as they are added to the service, they start to initiate transfers. The plot that is formed finally uh, tells us that the aggregate goodput of both the services as a function of time. And from this, we can observe that there is no considerable change in the aggregate goodput of the service one, even as the variable flows from service 2 joins the network. To further prove this point of performance isolation that is provided by the VL2 network, we consider a second experiment in which the service one is same is same and is same, and each server is transferring data to other server, whereas the service 2 creates burst, and each burst has different number of connections present. So again, from the second graph, we observe that the aggregate goodput of service 1 is unaffected by the service 2's activity. From both of these two experiments, we are able to demonstrate that the network architecture used is sufficient to provide performance isolation between services. We further work on evaluating VL2's response to, to a link or switch failure. The setup we use to experiment is we begin with an all-to-all data shuffle, and then we disconnect links between aggregation and intermediate switches until just one intermediate switch remains connected. This is just a test, and this type of mass link failures never occur in practicality. The resultant plots that are generated, from that we can observe that the network reconverges quickly in less than 1 second when there is a case of link failure. As you can see that after each dotted line, which represents failing links, the plot is able to reconverge in just less than 1 second. On the other hand, that is the right part of the plot, we observe that the link restoration is slow and takes over 50 seconds. However, not considering the time, the aggregate goodput is not compromised and it returns to its initial value. However, the time it takes is more and doesn't happen at instant, just like the failure links. So following the evaluation of all the properties that VL2 claims to provide, we now just want to answer some bonus questions. So in the paper that we were provided, was there any topic in the class that referred to the readings we found in the paper? So yes, the VL2 architecture maintains the routing between switches, and that is performed using the LA addresses using the link state routing algorithm that was also referred to in the lectures of the course. Further, what are the weaknesses that we believe existed in the paper and can be thought upon of more? So we observe that all the link and the switches are working all the time, and this is not at all power efficient. So we can work on an alternative where a more efficient method can be found. We can also try to work on some real-time performance analysis and not on just one prototype to evaluate the properties of the VL2. Also, in the case of VL2 directory system, it requires us to address some extra servers, which makes the system more cost inefficient and tough to implement. The next question we would like to answer is, what else can be done beyond the scope of the paper? So like commenting on the point of network security, the current system is vulnerable to cyber attacks. We can work on improving the security and making the systems more non-vulnerable. On the point of energy efficiency, significant amount of energy is consumed by VL2, and we can work on finding alternatives that are more energy efficient. In case there are some problems in the network, we can work on troubleshooting them in a more effective manner by building a more effective management.